Hello, everybody. Welcome to today's online lecture. Today, we are going to solve some problems from chapter 5, which talks about dimensional stability or dimensional analysis and stability. Before we proceed into the solving of problems of this chapter, let's understand few concepts that are quite important in this chapter. I'll go step by step, but let's start with understanding what do you mean by a dimension and what is its importance and what is its difference when you say a dimension and a unit. Dimension is a mode of measurement used by the basic uh, values like mass, length, and time and theta. Dimensions can be classified as basic dimensions and secondary dimensions. Secondary dimensions are dimensions that use basic dimensions, which are mass, length, time, and theta, and derive further to get the next set of variables. For example, acceleration is a ratio of length to the square of time. So it doesn't belong to the basic dimensions, but it is utilizing the basic dimensions of length and time to derive itself. Whereas if you have to measure a distance, it is measurement of length. You can call it as a basic dimension. Whereas when you have to measure velocity or acceleration, you use set of these dimensions to derive them. And the difference between dimensions and units is a quantity that you use to measure a variable. Like if you want to measure force, you measure it using newtons. But internally, that newton can be derived as a unit of kilogram meter per second square. This can be utilized in preparing a secondary dimension for force as a product of mass into acceleration, where mass uses a basic dimension of m and acceleration uses a secondary dimension of length to the ratio of square of time. So when you combine these two together, you get the dimension of force, which is mass times length divided by time square, or ml t to the power of minus 2. Let's solve a set of few problems from our textbook related to the dimensions. Problem 510, it has 4 parts. Let's try to write down the statement of the problem. The statement of the problem states, determine the dimension m l t theta of the following quantities. There are 4 parts of this problem. Part A, rho u dou u upon dou x. Part B, integral 1 to 2 p minus pa, P naught times dA. Part C, rho Cp dou square T upon dou x dou y. Part D, triple integral rho dou u by dou t dx dy dz. Let's start with the solution. Part A, which is rho u dou u by dou x. Let's try to break down each and every variable of this quantity. So rho is represented for density, and density is a ratio of mass upon volume. Mass can be represented in terms of a basic dimension m, and volume means measurement of length in x, y, and z directions. So you are measuring it in 3 dimensions. That would, let's say it as L cube. So this can be called as m L power minus 3. Similarly, the second part is part u, which we can call it as velocity. Velocity is a ratio of length to time. Length has a basic dimension as L, and time is represented by basic dimension t, which can be called as L t power minus 1. In place of dou u by dou x, let's break dou u by dou x into two segments. So I'll first find out what is the value of dou u. Dou u can be called as change in velocity, and even here, if you're moving from one point to another point, let's say point A to point B, and you're traveling from point A to point B, but over this period, over this distance, let's say from point A to A prime, you are traveling at x velocity, but from point x A prime to point B, you're traveling at y velocity. So there is a change in velocity, but overall from point A to B, you're traveling with velocity, with the velocity. It can have a change in velocity, but you're still representing that in velocity. So similarly, delta u, which is change in velocity, can be represented as length to time, which is again L over T, and that is equals to Lt power minus 1. Similarly, dou x means change in length. This can be represented by a basic dimension length. Let's call this as L. Now, once we have all these known variables represented as dimensions, substitute them into the basic quantity of rho u dou u by dou x, which is part A. Let's call this as equation 1, and substitute all these into equation 1. You will have rho u dou u by dou x is equals to m l power minus 3 multiplied by l t power minus 1 multiplied by dou u is l t power minus 1 divided by l. L and L gets cancelled, and you are left with this L gets cancelled with here, leaving minus 2. So your final answer would be m m l power minus 2 t power minus 2. So rho u dou u by dou x would be equals to m. You can either write it as divided by L square t square, or m L power minus 2 t power minus 2. Part B, let's try to solve one more problem, which is 1 to 2 p minus p naught dA. P minus p naught is nothing but change in pressure, and dA is nothing but change in area. If you look at this problem in a closed manner, delta P can be treated as a constant and can be taken out of the integral, leaving us with a constant value of integration with respect to dA. So integration of dA or delta A is A over the interval of 1 to 2. But still that interval of 1 to 2 will be nothing but area A. P minus P naught, which is equals to delta P, is nothing but a form of pressure, and that can be measured as force upon area. force is measured as mass times acceleration. And acceleration is represented as length to the square of time. That is equals to L over T square, L T power minus 2. Force can be written as M times of L by T square, or that can be written as M L T power minus 2. Area is equals to length square. That would be L square. Now you have all the details that are needed to solve this quantity. So integral 1 to 2 p minus p naught over dA is nothing but p times of A, which is equals to force over area times area. Integral 1 to 2 p minus p naught times dA is equals to m L T power minus 2 divided by L square multiplied by L square, and these two get cancelled, leading the answer to be integral 1 to 2 p naught dA is equals to m L T power minus 2. Let's try to solve part 3 quantity, which is rho Cp dou square T by dou x dou y. I can rewrite this equation as rho Cp dou by dou x times dou t by dou y. By referring table 5.1, page 296 of your textbook. Rho, we know, is nothing but density, can be written as mass upon volume, which will be equals to m upon L cube, that is equals to m L power minus 3. Cp is specific heat. This I have obtained it from the table 5.1, and it is represented as joules per kilogram Kelvin, and it the dimension representation would be, or yeah, the dimension representation would be L square divided by T square times theta. Delta x is equals to change in length is equals to L. Delta T would be change in temperature, and temperature is represented by theta, so that is equals to theta. Delta y is again change in length, which is represented as L. Overall, rho Cp dou square T by dou x dou y is nothing but rho Cp dou by dou x times dou t by dou y. That implies rho Cp dou square T by dou x dou y can be written as rho, which is m L power minus 3 times Cp, which is L square divided by T square times theta. Dou by dou x can be written as 1 divided by L. Dou t by dou y can be written as dou t is theta divided by L. Now, L and L cancel with L square. Theta gets cancelled with theta, leaving rho Cp dou square T by dou x dou y is equals to m upon L cube T square, or m L power minus 3 T power minus 2. Let's try to solve the next problem, part D, where we have triple integral rho dou u by dou t dx dy dz, which implies, here again if you observe closely, Rho, dou u by dou t are constants which can be pulled out of the integration, and it can be rewritten as rho dou u by dou t triple integral of dx dy dz. Rho is again mass upon volume for density, which is m upon L cube, can be written as ml power minus 3. Dou u is equals to delta u is equals to u, which is velocity, is L over t, or Lt per minus 1. Similarly, dou t is equals to delta t is equals to change in time, that is t, dx is change in length, that would be L. Also dy would also means change in length, that is also length, and dz is a change in length in z direction, which is also represented by L. Now we have everything, we just have to substitute these into the main quantity, which is triple integral rho dou u by dou t dx dy dz is equals to m L power minus 3 times dou u by dou t would be L t power minus 1 divided by t times L times L times L. L, L, L cancel with L cube, leading us to triple integral rho dou u by dou t dx dy dz would be equals to m L divided by t square, or m L t power minus 2.